Hi everyone! Today let's talk about section 7.1 to 7.3, linear first-order systems of differential equations. So this is the last chapter of our course. So we have learned linear algebra, we have learned first-order and higher-order differential equations. And today we're going to learn systems of differential equations. Okay, so here is an example. We have couple mass and springs. So here we have two mass and two spring. Okay, at equilibrium position, then they look like this. Okay, so this picture is at equilibrium position. Okay, and then when we apply to a force and then move this here and release, then those two mass and springs start to bounce off, right? And you can see, look at the first mass. So let x1, x2 be the displacements from the equilibrium position. So x1 is the distance from here to the equilibrium position. So this is the equilibrium position. Okay, and x2 is the distance of the second mass to its equilibrium position. So that is the equilibrium position. And then let's look at each mass. For the first mass, we have, if we set the right direction as the positive direction, and then the first mass, we have the force due to gravity, right? And we also have the supporting force from the ground, right? And then, for the spring force, we have a spring force from the first spring, okay? And the spring force equals to K times the, how much the spring stretch, okay, x1. So here we have the spring force, K1 times x1, and we also have another spring force from the second string. And how does this guy stretch? So M2 stretch x2 and then M1 stretch x1. So actually the total amount M2 stretch is actually, so this second spring, it actually stretch x2 minus x1. Okay? So if x2 move, if M2 move x2, centimeters, and M1 move x1 centimeters, and then how much the second spring stretch? It actually stretch x2 minus x1 centimeters. Okay, so the spring force here is K2 times x2 minus x1. That is the net force about the first mass. By the Newton's second law, we know Ma, which is the net force. So the net force is actually negative K1 x1 because the force is of the first spring is pointing to the left, so it's negative. And the second force pointing to the right is K2. Sorry, this guy should be 2. So K2 times x2 minus x1. Okay, so that's the spring force from the second spring, and it's pointing to the right, so it's positive. Okay, so that's the first mass. The second mass, we only have the spring force pointing to the left. Of course, it has the force due to gravity and the supporting force from the ground, okay? But they cancel out. So the net force is only the spring force by the second spring. So by Newton's law, the second law, we note ma. So acceleration is the second derivative of the displacement equals to, because this force is going to the left, so it's negative K2 times x2 minus x1. So now you can see this is actually a second order differential equations. Okay? And it's a system of differential equations. And another example, so notice that any higher order linear ODE can be written as a system of first order linear ODE. How does that work? Well, suppose we have a second order linear ODE, right? We can solve for y prime prime, okay? And then now what do? We defined x1 of t to be y of t, and we define x2 of t to be y prime of t. Then now what happened? Well, now x1 prime of t is y prime of t, which is x2 of t. But what is x2 prime of t? It's gonna be y prime prime of t. Wow! See, y prime prime is this guy. So that's why it's p of t. Y prime of t is x2 and plus q t. Y of t is x1 of t. And then plus f of t. So that's why you can see we have a system of first order linear ODE. Okay, it's linear ODE because you can see x1 and x2 there, and then the coefficients only consist of the functions of t. Okay, you don't have like powers of x1 and x2 or products of quotient of x1, x2, etc. Okay, so let's look at more example. So you can see now, because of this system of differential equation, on the left is actually the derivative of the vector x1 and x2, and then you can see if we consider the here we have the x1 and x2. Well, then look at the first. So look at x1. So the system, we can rewrite the system. So x1 of t is x2 of t. So it's like 0 times x1 of t plus 1 times x2 of t. Okay? So that's why we can consider the coefficient of x2 and x1, and we get this matrix. And x2, dx2 dt is q1 x1. So the coefficient of x1 is q of t plus p of t x2. So p of t right here. And then plus f of t. So this is actually the forcing function. So now you can see this is a system of differential equations, and we can have a matrix here. Okay, how about a third order differential equation? Okay, so we express the third order in terms of the lower order, right? We define x1 to be y of t, and we define x2 to be y prime of t. We define x3 to be y double prime of t, the second derivative. And then x1 prime is gonna be y prime is x2. x2 prime is y prime prime, which is x3. But x3 prime is gonna be y triple prime. Well, that is this guy. So it's p of t, y double prime is x3, plus q of t, y prime is x2, plus r of t, y of t is x1, and plus the forcing function, f of t. Okay. And now we can also write it in terms of a matrix. So on the left hand side, we have the derivative of x1, x2, and x3 with respect to t. And then on the right hand side, you can see we have the x1, x2, and x3 are like the variables, and then the coefficient functions. Well, look at the first one. We have 0 x1, so you put 0 here. We have x2, so we have 1 x2, and we have 0 x3. That's the first one, right? And for the second equation, we have x3. So we have 0 x1, 0 x2, and 1 x3. And then the third equation, we look at, okay, what's the coefficient of x1? Well, that is r of t. The coefficient of x2 is q of t, and the coefficient of x3 is p of t. So that's why we get this coefficient matrix. Okay, and then we still have f. F is the forcing function. Okay, so now we can consider x to be a vector. So x, this is x. X is x1, x2, x3 is a column vector. Okay, 3 by 1 column vector. And then on the left, we have the derivative of the x, the column vector x. And then let's call this matrix A. Then we have A times X plus, let's define F to be the column vector 0, 0, f of t. So now we can simplify and get this notation. Okay? Now we can use the same idea for first order linear systems as for the linear higher order equations. Okay? Because it's linear differential equation, we have a general solution. The general solution is going to consist two parts. The homogeneous solution and the particular solution. Okay, XH is the solution to the homogeneous problem differential equation. So it's the homogeneous solution, and XP is the particular solution depending on the forcing function f of t. Okay, and as before, the solution space of the homogeneous problem is the linear function space of dimension n, which is the length of the vector x, okay? And we need 3 linearly independent solutions to the homogeneous problem, okay? Because it's dimension n, so we need n linear independent solution. Okay, to generate the solution space for the homogeneous differential equation. Okay, and then next, how do we know they are linear independent? We can check Wronskian for the linear independence. Okay, and when a matrix A, so when A is a matrix of constants, there will be exponential solutions to the homogeneous problem. So in chapter 5, we talk about higher order linear differential equation with constant coefficients. Okay, if the coefficient matrix A only consists of constants, okay, so there's no t in it, then you kind of expect our solution will have exponential solution. Well, what's the exponential solution means? They can be like really exponential solution, like e to the 5x. They can be polynomials, because polynomial corresponds to like e to the 0 times x, right? So we consider that as exponential function with the r is 0. And also we have the complex exponential function. So, remember e to the 2 plus 3i, okay? This will give us forget the x. This will give us e to the 2x cosine 3x, plus c2 e to the 2x sine 3x. So we call this guy like complex exponential function. Okay? So if the matrix A is a matrix of constants, we kind of expect our solution is in the form of these. Okay? And for the non-homogeneous part F, we can use undetermined coefficients or variation of parameter to find the particular solution. But in our course, we only talk about the method of undetermined coefficients. Okay? Alright, so first of all, how do we find the homogeneous solution? Okay, so now look at our system. So here, homogeneous, so it means the f is 0. Okay, so we have x prime equals to a times x. Okay, so now we also suppose that A is only a matrix of constants. Okay, so in our course, we only consider linear systems with the coefficients matrix just constants. Okay, so that's why we expect our solution in terms of exponential function. So let our solution be v of t times e to the lambda t, okay, where v is the vector of constants, and we need to find both v and lambda. Okay, so x, so let's plus x in it. X is v e to the lambda t, right? Okay, so what's x prime? So when we differentiate it, because v is a constant just stay here, and then derivative of e to the lambda t is lambda e to the lambda t. So far so good, everybody. So now let's plug into our differential equation. So x prime is lambda v times e to the lambda t, and then we have a times x. X is v times e to the lambda t. Okay, and now you can see I can both sides, let's subtract lambda v e to the lambda t from both sides. Then we have 0 on the left. On the right, we have a v e to the lambda t minus lambda v e to the lambda t. Okay, you can see we have the common factor e to the lambda t. Let's factor that out. What do we get? AV minus lambda v. Okay, because the exponential term is always not 0, okay? So that's why in order to make this guy equal to 0, the only way is to have AV minus lambda v is 0. Well, what does that mean? Remember, AV minus lambda v is 0 is the same as saying AV equals to lambda v. It means that lambda is an eigenvalue for A, and v is an eigenvector associated to lambda. Okay, so that's why we need to study the eigenvector and eigenvalues in chapter 6, because it will help us to solve a system of linear ODEs in chapter 7. Okay, so this is the algorithm. First, we want to find the eigenvalue and eigenvector for the matrix A. Okay, so we solve the characteristic equation determinant of A minus lambda I equal to 0 to find the eigenvalue lambda. And then for each eigenvalue lambda, we solve the linear system A minus lambda IV to find the eigenvector associated with lambda. Then the homogeneous solution is C1. Let's say our A is 2 by 2. Okay, if our A is 2 by 2, then the homogeneous solution is going to be C1 V1 e to the lambda 1t, because remember our solution looks like this, V times e to the lambda. So that's why we have V1. V1 is the eigenvector associated with the eigenvalue lambda 1. And V2 is the eigenvector associated with the eigenvalue lambda 2. That's why if we have two complex roots, then they look like that. Okay, so depending on the number of eigenvalues and eigenvectors. Okay, so here is our algorithm. Okay, so suppose we have 2 by 2 matrix, then we get 3 cases. We can have 2 real roots, we can have 1 repeated root, or we can have 2 complex conjugate roots. So today we're gonna look we're gonna see all of those 3 cases, okay, and how to solve those examples. Okay, first case, we have 2 real roots. Example 1, solve the initial value problem, first order homogeneous differential equations with constant coefficients. Okay, so this is the system of linear ODEs with the initial condition x1 equals to 2, okay, x2 of 0 equals to minus 1. Okay, so what do we do? I'm going to rewrite it. So I'm going to rewrite this as x equals to, so x is x1, x2, right? So let me put it here. Okay, then this system is the same as the derivative of x equals to, you can see the coefficient 5x1 minus x2, 3x1 plus x2. So this is what it looks like, okay? And we call this matrix A. Okay? So the first thing we need to do is we need to find the eigenvalue and eigenvector for the matrix A. So this is similar to what we have done in chapter 6. So first step, we compute 0 is the characteristic equation, the determinants of A minus lambda I, that is you subtract lambda from the diagonal element and all the other entries stay the same. Okay, so what is that? Well, because this is a 2 by 2 matrix, we cross multiply. So, but don't forget, we subtract. So 5 minus lambda, 1 minus lambda, and we subtract 3 times negative 1. Okay, what is that? Well, let's multiply out. 5 times 1 is 5. 5 times lambda, so minus 5 lambda. And minus lambda times 1 is minus lambda. And we also have plus lambda square, right? Negative 3 times negative 1 is positive 3. And let's reorder it. So that's lambda squared, and minus 5 lambda minus lambda is minus 6 lambda. And 5 plus 3 is 8. So this is our characteristic equation. Okay, we're gonna solve for lambda. So here we can actually factor it. We have minus 4 and minus 2, right? So here we have lambda is 2, and here we have lambda equals 4. So far, so good. And then for each eigenvalue, so these are the eigenvalues. For each eigenvalues, we need to find the eigenvector associated with it. Okay? So next, step 2, let's see when lambda equals to 2. Let V be xy. Okay, I know it's a little bit abuse of notation. My x looks like my vector x, but if I don't put an arrow there, I mean it's just x. Okay, if I put an arrow on top, I mean this is a vector. Okay, so we want to have A minus lambda I times V equals to 0. Okay, what is the augmented coefficient matrix? Well, A minus lambda I, 5 minus lambda give us, so 5 minus 2 is 3. And then 1 minus 2 is minus 1. Oh, you can see what happened? So we can use negative row 1, add to row 2. So remember when you find the eigenvectors, when you solve the augmented coefficient matrix, you realize the last row is always 0. Okay? So if you don't get 0 in the last row, then there must be something wrong, and then go back and check your work. Okay? So this is x, this is y, this is the right hand side. The first row tells us that 3x minus 1y. Okay, so 3x minus y is 0. Then what is x? Well, x, we move the y to the other side and divide it by 3. Okay, so v is then xy. Well, x is y over 3. So now we can pick y to be 3 because in that case we can have integer entry. Then our answer is 1, 3. Okay, so this is eigenvector associated with the eigenvalue lambda equals 2, right? Okay, next we have the lambda equals 4. Let's solve for it. Okay, you can pause the video and try to solve for it first. After you're done, we can check our work together. Okay? So, the augmented coefficient matrix, 5 minus, what's the matrix? 5 minus lambda. Lambda is 4, so 5 minus 4 is 1. And 1 minus 4 is negative 3. Okay, can you see the second row is the multiple of the first row? So we use negative 3 R1 add to R2. and then we get zeros. Okay, so this is x, this is y, this is the right hand side. Alright, and then let's plug in the first row. We have x minus y equals 0. Well, x is y. So v is then xy, but x is y. We can pick y to be 1, and then our v is then 1, 1. So this is the eigenvector associated with the eigenvalue lambda equals 4. Okay, so now we have 2 eigenvalues and 2 eigenvectors. What is the solution? Well, then the solution, remember, the solution is in the form of the eigenvector times e to the eigenvalue t. Okay, so the solution, x of t equals c1, the first eigenvector, which is 1, 3, e to the, what's the eigenvalue? 2t, right? Let me see. Alright, yes. And next, we have C2. The second eigenvector is 1, 1. That the corresponding eigenvalue is 4. Okay, so this is the solution. Okay, so this is the solution, and then how do we find the C1 and C2? Well, we have the initial condition, right? Our initial condition is 2 and minus 1. So x of 0 is 2 and minus 1. Okay, so let's plug in it. So we plug in t is 0, we get c1, 1, 3, e to the 0 is 1, plus c2, 1, 1, and that equals to 2 minus 1. Ooh, so it's the same as we want to solve the matrix 1, 3, 1, 1, and 2 minus 1. Okay, this corresponds to C1, this is C2, this is the right hand side. So we can use negative 3 R1 add to R2. Then we have 1, 1, 2. 3 minus 3, 0. 1 minus 3, negative 2. Negative 1 minus 3 times 2. Negative 1 minus 6, which is negative 7. So far, so good, everybody. So we get, this is C1, this is C2, this is the right-hand side. And then negative 2 C2 is minus 7. C2 is 7 over 2. Then we plug in the first row. First row give us C1 plus C2 is 2. Okay, so then C1 is 2 minus C2, which is 2 minus 7 over 2. Well, that is like 4 minus 7, so negative 3 over 2. So finally, our solution is C1. C1 is negative 3 over 2, and then we have 1, 3, e to the 2t, plus C2. C2 is 7 over 2, 1, 1, e to the 4t. So this is our solution. Well, you might ask, then what is x1? What is x2? Well, this is the same as saying x1 of t is, you look at the first row, okay? So we get negative 3 over 2 e to the 2t plus 7 over 2 e to the 4t. And x2 of t is, you look at the second row. So negative 3 times 3 is 9 over 2 e to the 2t plus 7 over 2 e to the 4t. So far, so good, everybody. But you just need to, I should use a darker color. Sorry about that. So this is, you can just write your solution in this form. Okay, I write this just to let you know, if sometimes you want to know what's x1, x2, they are x1, x2. X1 is the first entry of the x vector, and then x2 is the second entry of the x vector. Okay? Alright. Let's continue. So you can pause the video here and try to work on example 2. Are you done? Let's check our work. So we define x to be x1, x2. Then this is the same as x prime is minus 2x1 plus 4x2, 1x1 plus 1x2. This is the matrix A. So far, so good. Okay, then the first step, find the characteristic equation. Right, so A minus lambda I. So subtract lambda from the diagonal elements, and the rest entry stay the same. So cross multiply minus 2 minus lambda, 1 minus lambda, minus 1 times 4. Yeah, cross multiply, but subtract, okay? So let's see. Negative 2 times 1, negative 2. Negative 2 times negative lambda is plus 2 lambda. Negative lambda times 1, negative lambda. Negative lambda times negative lambda plus lambda squared, minus 4. Let's reorder it from the highest power, lambda squared, and then how many lambda? 2 lambda minus lambda, that's lambda. Negative 2 minus negative, so negative 2 minus 4 is negative 6. Okay, so this is the characteristic equation. We want to solve for lambda. So it will be plus 3 and minus 2, right? So this gives us lambda is 2, and this gives us lambda is negative 3. So we have two distinct real roots. So when lambda equals to 2, what is the... So we let v be xy, okay? We want to solve a minus lambda I times v equal to 0. So what is the augmented coefficient matrix? We use matrix A, subtract lambda from the diagonal elements. So minus 2 is minus 4. And then we have 4. 1 minus... Where do I look at? I look at here. And I plug in lambda equals to 2 there. Okay, so 1 minus 2 is negative 1. And the right hand side is 0. Okay, you can see I can factor out, I can divide it by 4 because all of them have the factor 4 in the first row. And then I can use the resulting row 1 add to row 2. So here I'm actually combining two steps into a step. Yes. So then I have x, y, and this is the right hand side. The first row tells us that minus x plus y is 0. Oh, then x is y. So v is then xy. X is y. So we can pick y to be 1. The eigenvector is 1 and 1. So this is the eigenvector. Correspond to the eigenvalue. Lambda equals 2. Okay. Let's continue. Lambda equals negative 3. Okay, so v is xy. What is the augmented coefficient matrix? So negative, so look at this guy, right? Negative 2 minus negative 3 is like negative 2 plus 3, so 1. And then we have 4. 1 minus negative 3 is like 1 plus 3, so 4. Oh, you see? We always get the second row 0. That's always the case. Then we have x, y, and this is the right-hand side. This guy tells us that x plus 4y is 0. So x equals to negative 4y. Okay, so v is then x is negative 4y, y. Well, we can pick y to be 1. Then v is negative 4, 1. This is the eigenvector associated with the eigen value lambda equals to negative 3. Okay? Alright. So what is our answer? Well, that's C1. The first eigenvector, 1, 1, e to the first eigenvalue, 2t. C2, the second eigenvector, e to the second eigenvalue, t. Okay, so this is the answer, and we need to find C1 and C2. So what is our initial condition? Negative 2 and 3. So we plug in negative 2 and 3 there. So we plug in t is 0. Okay, so we get C1, 1, 1, e to the 0 is 1. C2 minus 4, 1, e to the 0 is 1. And we have negative 2 and 3. Well, that is the same as to solve the augmented coefficient matrix 1, minus 4, and negative 2, 1, 1, and 3. Okay, so this is the coefficient, the first column are the coefficient of C1, second column are the coefficient of C2, and then the last column is the right-hand side. Okay, so we use negative row 1 add to row 2. Then we have 1 minus 4 minus 2. 1 minus 1 is 0. 1 minus negative 4 is 1 plus 4, which is 5. 3 minus negative 2, 3 plus 2, 5. So this is C1, C2, this is right-hand side. Oh, 5 C2 is 5. What is C2? 1. So, and then C1 minus 4, C2 is negative 2. Then C1 is 4 C2 minus 2, which is 4 minus 2, which is 2. So what is our solution? Our solution C1 is 2. So 2, 1, 1, e to the 2t, plus C2, C2 is 1. Negative 4, 1, e to the negative 3t. So this is our answer. So far, so good, everybody? Yes. So here are the two real root case. Alright. In the video part B, we're gonna talk about two complex root case. Okay, let's continue on in video part B.